Bismillahirrahmanirrahim. Welcome all of you to the seminar on basics of LNA design. And in this seminar, we will talk about the basics of LNA from very core basics concept. And then we will discuss some advanced application like software-defined radio and kinetic review application. What type of LNAs are required in there? Outline of presentation. The part one will be the introduction and motivation, that what kind of communication standard we are using nowadays and how LNA fit into these communication standards. LNAs are the first part after the first component after the antenna in all kind of radio systems, because the signal is very weak and we need to amplify the signal after the antenna. So this is the variety of LNAs which are available and in the market, which are employed on these applications. So in the first part, we will talk about the introduction and motivation. We will talk about the market of the radio devices. We will talk about the wireless standard, then 3G, 4G mobile anatomy, recently what type of mobile phone we are using, and then we will talk about the 5G standard which is coming up, and then we will talk about that what are the requirements of the LNA for this software-defined radio and cognitive radio, which is actually a 5G standard. In the part two, we will go to the basics, some basic definition of noise figure, linearity, dynamic range. We will discuss in part two, and in part three, we will talk about the narrowband LNAs and multiband LNAs and wideband LNAs. So we will see that in which situation we imply which type of LNA and what are the basic trade-offs dealing with this different type of LNAs. And then at the end, we will talk about the two case studies, which are actually my two designs and LNA we designed in the past. And I will discuss the design of those two LNAs. They are published in different IEEE journals. So we will take these LNAs as a case study. So let's start from the electronics market. The electronic system market is now more than a $3 trillion, and this data is from the 2021, just the last year data. And amazing part of this is that this market is increasing by 4% every year. So out of this electronic system market, the market of wireless devices is huge, and especially with the advent of the IoT, that every device, electronic device, will be interconnected with the network and it will be controllable and talking to you. This has given rise to the exponential growth in the wireless market. So if you just talk about the mobile phone sales, just the handset, this mobile handset, I'm not talking about the IoT devices, just the mobile handsets. In 2019-20, around the globe, the 1.52 billion mobile set was sold. And these mobile sets include this different radios. A simple mobile has 5-6 different radios, which are the GPS, the Bluetooth, the wireless LAN, the GSM, the LTE, the 4G. So the typical handset has a 5, 6 or 7 different radios in it. So the total sale was around 1.52 billion, and that makes a 4.6 million mobile devices every day. This is a tremendous market for the mobile devices. If you look at the reference to the Pakistan, we have the population of 230 million people, and we have almost 16 million users already in Pakistan, and some of the users, they have more than one mobile device. So how many of you have more than one mobile? Can you raise the hand? Or you have the more than one mobile sets in last 2 years? Which, okay, 1, 2, 3, 4, 5. So 5 people have more than one mobile set. So this is the number of mobile devices we are using in Pakistan. So up to 90% of the world, 7 billion population will be have a mobile telephone coverage by 2025. And this is a reachable goal, because you see that the Starlink satellites from the Elon Musk, they are providing the interconnectivity of the internet to those remote areas of the globe which were not accessible by other means. So in up to 2025, rather more than 90% of the world population will be connected with the internet, and that connection is of course through the mobile devices. So let's have a quick view of the wireless standard. So we started, the basic wireless standard was DECT, which is the wireless phone, and then the basic 1G was the GSM, the first digital standard. And then it evolved to 2G, 3G, 4G, and nowadays 5G. So what is the basic difference between this standard on the user side? So on the user side, the basic difference is the data rate which these standards can carry. So if you look at this one, so let me open up this laser pointer. So if you look at this, we have a 1G 2.4 kilobit per second, 2G 64, it increased, then it was 2 megabit per second, then it was a 4G 100,000 kilobit per second, and now in the 4G it's a 1 gigabit per second, and it's for 5G it's a 1 gigabit per second to 10 gigabit per second and 100 gigabit per second depending upon the scenarios. So what are those scenarios which covers this standard? That the coverage, bandwidth and latency, they are a trade-off between each other. So if you look at this one on the top, you have a higher bandwidth which are millimeter wave, and these are in the 5G. So when you need a very high speed like 1 gigabit per second or 10 gigabit per second, then you cannot use the, for example, GSM is using 900 megahertz. So on 9 megahertz carrier frequency, you cannot transmit 1 gigabit per second. Okay, your data rate cannot be more than your carrier frequency. So if you want to go to the higher bandwidths, your carrier frequency has to go up. So that's why in the millimeter, in the 5G, the major 5G standard is defined by the sub 6 gigahertz frequency. But they have also introduced the higher bands, which are millimeter wave frequency, which can support the data rate of 1 gigabit per second, 10 gigabit per second, or even higher than that. So the trade-off between these are the low bands, mid bands, mid-band 2 and high band. And if you see, if you talk about the number of size of the cell, so for the gigabit communication, the cells are called the pico cells. They are very small in size, and the transmission and reception distances in hundreds of meters, not in kilometers. And on top of it, they are using the beam farming just to concentrate the energy in one direction so that higher data rate can be supported within the shorter distance using the lesser power. Otherwise, the power requirement will be so large that this bandwidth will not be supported. So here is the 5G releases from the release 5, release 7 is release 5, release 6, and then release 7. So these are the different use case scenarios that some of the applications are talking about the IoT and connectivity with the IoT devices. The other operation is a real time. For example, a surgeon is performing a surgery at a remote location. So then the latency should be minimal, the data rate should be very high, the resolution should be high. So this is the different application scenarios which are being covered in this 5G standard and its different releases. So if you look at the mobile phone you have right now in your hand, like this mobile set, you have a Bluetooth, you have a GPS, you have a GSM, you have a WiMAX, you have a Wi-Fi 802.11, and you have a LT. WiMAX LT is the 3G, 4G standards. So these are the, you say 1, 2, 3, 4, 5, 6 radios which are present in any mobile smartphone you have in your hand. So these 6 radio are different radio standard, and they have a different hardware which is present in the mobile. So if you look at a typical scenario, like you have a 6 radios and you have a 6 different antennas, because these radios are working at a different frequencies, and then you have a different chipsets for the different standards, and then you have a baseband processor where the data is down converted and A to D conversion, and then the baseband processor can be common, but then you cannot use all 6 radio at one time. Then you have application processor, which is controlling your camera or keyboard, display, speaker, and giving you the other user interface signals. So if you look at the mobile phone, you have this mobile phone PCB where you find this all radios marked here. So your GSM radio, your Bluetooth radio, your GPS radio, and they have in the same space, they have the RF chipsets, and they also have the power amplifiers which are dedicated to each standard. So actually today's information companion, which is a 4G mobile phone or 3G mobile phone, it's a very complicated device. So if you look at a Nokia 6280, this is a 3G mobile phone. So you see here the number of devices, number of LNAs, number of filters. The antenna is common, and then you have a duplexer, time domain switch, and then you have a filters, and then you have a number of LNAs, number of mixer, and then baseband processor. So this is a typical architecture. If you So if you go to the Apple iPhone, so if you see here, there's a lot, this all chipsets which are placed here in a PCB, which is a very complex multi-layer high frequency PCB. You see all kind of standard here, which is the chipset for the power amplifier for the different standard, and chipset for the LNA, and the processing, RF processing for the different standards. So this is a typical diagram here, which this is the hardware. The previous slide was the hardware, and this is the typical diagram. You see here, I have highlighted the number of LNAs here and number of LNAs there. This is the number of no noise amplifier used in any kind of the current mobile device you have. So we are using the 7-8 different low noise amplifier in our information companion. Why not to use a one LNA and one power amplifier and make it a wideband so that it covers all the standards? So if we could do that, that concept is called software defined radio. And what advantage the software defined radio will have? Of course, the cost will be reduced, and it will be tremendously reduced. The space on the PCB will reduce, the power consumption will be reduced. So this was the concept basically introduced by J. Metola in Royal Institute of Technology in Stockholm in 1990s, and this was his first paper published where he introduced the software defined radio. So it looks very attractive from outside, that you have an antenna here, and then you have a LNA, you amplify whole the spectrum from 1 to 6 gigahertz, and then you put the A to D converter here, and then you digitize it, and then you bring the data in baseband processing, and then you have a laboratory of the DSP, and you do that, hold the processing in the digital domain. Very nice concept. And what's the problem with it? For example, let's look at the standard. So if the GSM is at a 900 megahertz, Bluetooth is at a 2.4 gigahertz, A to D data 11B is at 5.4 gigahertz. So we have a bandwidth of say something like 900 megahertz to 5.5 gigahertz. So if we have to imply the A to D converter here, so this means higher frequency will be 5.5 gigahertz, and we need a A to D converter based on the Nyquist sampling, which is 11 gigasample per second. 11 gigasample per second. And say the A to D converter we have is say 10 bit or 12 bit. We are not going for 14 bit. So we need a 12 bit converter with sampling rate of 11 gigasample per second. So if we do this directly, and then we have the DAC which has a 11 gigasample per second DAC and to cover the same bandwidth. So if we can have this A to D and DAC, yes, of course, we can make a software-defined radio. But practically, when we try to implement with the today's technology, which is 45 nanometer CMOS or 28 nanometer CMOS, what we see is that instead of this software-defined radio, you see here, this is software-defined radio. So this guy need a car battery to carry with it to power this software-defined radio. Because at this high frequency, at this high sampling rate, and with this high resolution, the A to D converter will be consuming a lot of power. So this is not a feasible. With today's technology, we don't have a A to D converter which can run from a 250 milliampere hour battery, which we have in this type of mobile phone. So power consumption become the prohibitive thing in this case. So we cannot use this technique correctly. So what to do? So this means the major challenge is that after the LNA, we need to have some kind of frequency translation so that we have an antenna, we have an LNA, the signal, weak signal is amplified, and then we translate it down, and then we use the A to D converter just to reduce the sampling rate of A to D converter. So this is a realistic SDR where we have a RF filters, we have a LNA, so we amplify the weak signal, and then we have some kind of frequency translation. And then after this frequency translation, our sampling frequency of A to D converter will be smaller and our power consumption will be lower. So this is the different type of ingredient we can apply here. Here we can apply a multiple narrowband LNAs. We can apply multiband LNAs. One LNA is doing multiple bands, but it's not wideband. We can apply the wideband LNA. So this is the three type of LNA we can have in the front end. Similarly, in the mixer or sampling stage, we can have a classical analog mixer with the analog filter. We have a sampling and discrete time filter, which is implemented using the switch capacitor filter. And then we can have a sampling and then high frequency sigma delta type of the mixer. So this is the three kind of mixer we can have. Is the mixing stage, which is basically a frequency translation stage. And then at the AD converter, we can have a normal ADC, which is a flash type of ADC, or we can have a sigma delta type of A to D converter, or successive approximation type of A to D converter, any type of A to D converter which are feasible for our design. So this is the realistic SDR. I hope it's clear to everyone. Yes. Now let's see the spectrum. Spectrum is the most expensive resource nowadays. The governments do the auction of the spectrum worth billions of dollars because the frequency, the mobile companies, they pay for the frequency, a huge amount. So spectrum utilization should be very, very efficient. So the spectrum of the different standard is already sold around the globe, and that is basically controlled by the FCC, which is the spectrum control. So if you look at the USA, it shows that 70% of the allocated spectrum is not utilized. So all the spectrum which is given to the different application is not used all the time. So this means if the spectrum is not used all the time, why not to sense that spectrum and use it? Because there's no new frequency available for the new application. So what the people have proposed that you sense the spectrum. For example, when you switch on the device here, you sense the spectrum around. And you see that which frequencies are being used by different applications. For example, here in the airport authorities are using the one application, the Islamabad police is using one frequency, the safe city is using another frequency, the GSM is using another frequency, the Bluetooth is using another frequency to sense the frequency in the environment, and irrespective of that, these frequencies are allocated to certain application. That allocation will diminish, and if the transmission in that frequency is not there in the environment, use that frequency. But there will be limit on the power transmission, that this do not pollute the legitimate user which is somewhere else, say 10 kilometers away from this. So this concept is called the opportunistic spectrum sensing, and that's both in a time domain and a frequency domain. Some transmitter can be transmitting for the 10 seconds and then go away. Some transmitter can be using one frequency at a time and then go away. So we are sensing both in the frequency domain and also in the time domain. So what is a cognitive radio? The cognitive radio is a kind of a radio, RF technology, that listens to the huge swath of the spectrum and then has a knowledge of the primary user, and then primary user and also the location and time. And then it has a set rules which are approved by the government to engage that spectrum for its own transmission. And that's a solution to the scarceness of the spectrum. And this concept is called the cognitive radio. So what's the requirement of cognitive radio? The first requirement that this cognitive radio should exist with the legacy radios. So if you are using the cognitive radio, it's not that all your previous devices should be shut down. User uses their spectrum resources and does not interfere with the already existing standards. So we will skip this slide. So what's the primary objective of the cognitive radio? Increase spectrum availability through coexistence, understanding of the roaming between the network and services. Third one is the reduced user control burden and dynamic regulatory compliance. This is a key word. That you are compliant to the regulatory authorities, but that compliance is dynamic. So if you move your radio from a urban environment where spectrum is much more used in the different application to the rural environment, in that case, your cognitive radio will be working more better with the more low-cost resources. So the second aspect of the cognitive radio is the cost optimization. How you will do the cost optimization? Like if you have you want to access the internet and you have 3 different routes. For example, you can access through your 4G radio, you can have access through your WLAN, and then you can have access to the 5G radio from the Starlink, which is the satellite radio. So then your cognitive radio have the intelligence that it will utilize the resources which are most low cost and available at that time. And if the low cost resources are not available, then it will switch to the high cost. And then not only the switching between the one low cost network and another high cost network, it will be able to send some of your data on a low cost network and your bandwidth is utilized, which is available. And then it use the remaining data and send it the next higher costly network so that your monthly bill is optimized. So this is the cost optimization functionality of the 5 cognitive radio, which will be built into the cognitive radios. So these are the different application of the cognitive radio. Defense is the one of the major application in this area. So this is the realistic SDR, which is that we have a frequency translation and then we have a. So let's talk about now a kind of that if we are having a new kind of radio which can address all these standards, what type of technology will be using? Technology means where you will implement it. We have a lot of available scenarios for the technology, which is a CMOS, gallium arsenide, indium antimonide, gallium nitride, different type of the transistor. Which technology is most suitable for the SDR? So the answer is very, very simple, because the baseband processing required for cognitive radio is demand of the processing power is very, very high. and we cannot make the processors in other technology except the CMOS. So the most efficient processor we can make are the CMOS. So our natural tendency is to use the CMOS technology for the radios as well. Previously, 15-20 years back, there was a big problem using the CMOS technology because FT, which is a unity gain band frequency for the CMOS, was very, very small. So if you go now to the recent technology, you see that the FT of the 16 nanometer is 730 giga, and the nominal voltage has scaled down. So FT is a key parameter which determines the frequency of operation. For example, in the 5G, we have a 28 to 32 gigahertz band, millimeter wave band in 5G, and we want to design a front end for it. So if you go look at the FT, it's a 730 gigahertz for the 16 nanometer CMOS technology. So usually, this, as we discussed in the class, usually we can comfortably design the amplifiers and related circuit and GM cells and the filters for the FT by 10. So if we have a 730 FT, so at 73 gigahertz, we can comfortably design. People have came up with the design wherein they have designed the 60 gigahertz circuits in a 65 nanometer technology. So you can push this limit hard, but as a rule of thumb, FT by 10 is a good number to start with. So we can do all the millimeter wave design in the coming 5G technologies in a CMOS. So CMOS is a major technology which is being used for this kind of radios. So this is what I explained. So that voltage scaling is 1.2 to 1 volt, and then the peak FT from 270 gigahertz, it has gone to 730 gigahertz for a 16 nanometer. So there's a lot of room. So what is the problem? The problem of CMOS is 1 over FNOES. So CMOS transistor is inferior to the bipolar junction transistor inherently. Bipolar junction transistor has a higher gain for the same power. It has a better 1 over FNOES characteristic. So these are two big plus for the bipolar junction transistor. But we will not be using the bipolar junction transistor for this kind of design due to other reasons, which are actually digital baseband processor. And for the cost, we want to do all the things in a single chip. So this was the introduction part. So now I will be switching to the second half of the seminar, which is the back to the basic and some basic definitions about the low noise amplifiers. So I hope the people, if someone is on the net, then they are getting my voice and slides clearly. So the audience who has remotely logged in and they are following this seminar on the internet. So please, if there is some jitter in the slides or my voice or the video, so please send a text message and then we will mitigate it. So the first thing which we define about the LNAs, low noise amplifier, are different from the amplifiers. So what is the basic difference? They are low noise. So the first thing we would like to measure is their noise figure. So how we define the noise figure? So this is the input spectrum, which is coming on the antenna, and this is a signal and this is a noise floor. So you see here, there is a peak minus 60 and noise floor is at a 100. So what's the noise, signal to noise ratio here? 40 dB almost. So when this is amplified, here we have an amplifier. So the gain is 20 dB. So, and the noise figure of this is 10 dB. So when it's amplified, what we get is our noise and signal both are amplified. So noise is amplified from minus 100 and 20 is gain. So noise has gone from minus 100 to minus 80. This is 20 dB amplification in noise. And then we have 10 dB of additional noise coming from the LNA itself. So that's a nice figure. And then we have an amplification of the signal. And then signal is amplified from -60 to -40. So this is the over amplified output. But this is very important to note down here is that at the input the signal to noise ratio was 40 dB and output signal to noise ratio is how much? 30 dB. So whenever we pass the signal from any kind of amplifier, the signal to noise ratio degrades. The signal gets powerful, the signal is amplified, but signal to noise ratio is degraded. The second thing we will have is noise figure definition. This is a noise floor, required signal to noise ratio. This is noise figure, and this is a path loss. This is coming from antenna. And if we represent it in a dB, it's called noise figure. And if we represent it in a linear scale, then we call the noise factor. The second thing is the sensitivity. So what is the sensitivity of a radio? The sensitivity of radio is defined as minimum detectable RF signal at input. So if we have a GSM radio, the standard defines that if the GSM signal is at -102 dBm, it should be detectable and we should be able to have a nice quality voice call on this signal. So this is called the basic sensitivity. How it relates with the noise figure? So you see here that this is the limit, receiver thermal noise limit, and then you have a noise figure here, and then you have an amplified signal. So if the signal to noise ratio is less than say 10 to 15, generally for a good bit error rate or good voice quality or bit error rate less than 10⁻⁻3, signal to noise ratio in different standards should be between 10 and 50. So we have to meet this signal to noise ratio dB here in 10 to 50, and then noise figure of receiver should be as low as possible to give us a higher sensitivity, because this KTB noise is fixed. So KTB noise is coming from the thermal noise, and this is a thermal noise floor, so this is fixed. The next thing is the selectivity. So selectivity is that we have a number of channels in all the standard. So ability of receiver to accept a given band and reject the unwanted interfering signals. All the bands which are not desired in the radio, they are called the interferers. So our desired band is here, the green one in the middle, and the adjacent channel where your friends are transmitting. If I am making a call on any of the radio standards, then I am transmitting in a certain channel, and my neighboring channel are used by some other people. So the selectivity is the receiver ability to reject the neighboring band and listen to the desired band. And this is usually in the standards, this selectivity is not given in terms in like a previous slides. It's defined in terms of the blocker profile. So the standard defines that your desired signal is -99. So my signal is very weak. My neighboring signal are powerful. So my receiver should be selective enough that my receiver should have enough filtering that I can listen to this -99 dB signal in presence of all the blockers which are shown here. So these are called in-band blocker, and these are called the out-of-band. There are two types of blocker. The in-band blocker are out-of-band blocker. So I should be able to listen to my signal in presence of both the blocker, and that directly relates with the filtering quality of the receiver. Narrowband filters mean better filtering quality with a high Q factor, then my selectivity will be better. And this will translate to the wideband LNAs, that in case of wideband LNA, blockers desensitize the radio. Because when the blockers come in, we will see the radio will not be working. So basic channel selection is now depending upon, as I said, filtering. So there are two type of filter. One are the filters at RF front end, and other are the filter at after the down conversion, which is called intermediate frequency filtering, and they both filtering combined together defines the channel selection. So basic sensitivity with selectivity. Sensitivity and selectivity, they are trade-off with each other. So if you make one higher, the other is compromised. The last basic thing is the dynamic range. So dynamic range is the ability of the radio that how small signal it can detect and how big signal it can tolerate. So when the signal will be powerful, the LNA will saturate. So the difference between these two, the smallest signal which is detectable and the highest signal which is tolerate, is called the dynamic range. So dynamic range, and the last thing is the linearity. So if input is a sine wave, the output is sine wave, this means the LNA is linear. So if you have a sine wave and you have a single frequency, if you have a very high gain and you are close to the power supply, instead of one tone, you will have a multiple tone here, and that is actually, instead of the sine wave, you will have a fundamentals and the cross intermodulation distortion coming in here. So linear LNA mean more clean amplification. So basic measure of linearity, we have two basic measure of linearity. One is called 1 dB compression point, another is called IIP3. So the last basics is the Frisch formula. It says that how the noise figure and linearity relates. So if you have a LNA here and you have some second block here, so if you put two blocks together, the total noise figure is equal to the noise figure of LNA, the noise factor of the second minus 1 divided by the gain of LNA. So this means the dominant noise figure is coming from the first block. First block has a dominant noise. The other blocks after the LNA doesn't contribute much to the noise figure, and this is a fundamental concept of the LNA. That's why we focus on the noise of LNA and we don't focus on the noise of the mixer and the other blocks. The linearity is just opposite. So in the linearity, the things become non-linear when the desired signal is large. So in LNA, the signal is very, very weak. So there's no much issue of non-linearity. But when LNA amplifies the signal and the signal is powerful, so to the second block, there is a chances of saturation. So in the Frisch formula, we say the total IP3 or total non-linearity is equal to the inverse of the first non-linearity and then gain multiplied by the other. You see the gain is multiplying with the second factor. So this means in this blocks, for the total radio, the noise figure of the first one matters and the linearity of the last one matters. So if we want to have a highly linear radio, then the linearity of the blocks after LNA should be higher. And the noise figure of the first block, which is LNA, should be lower. So then is last one is the matching, that we need to do the matching in order that signals are not reflected. If we will not match properly, if the interconnect length is comparable to the transmission frequency, so the lambda which we are transmitting and the interconnect length is say lambda by 10, the reflection will not occur. But if the interconnect becomes more bigger than lambda by 10, then there will be a reflections. And in that case, we need to do the matching, and we do measure the matching by S parameters, which S11 and S22 are the parameters to measure the matching. So this was basics of the LNA. The last thing is that when we do the matching, we have two type of noise figure. One is the noise figure coming when we have a power match. And other noise figure will be minimum when we have a noise match. So for to avoid the reflection in a power, we have to do the conjugate power matching, and this will give us a noise figure. And if we have a noise matching, then we will get a noise figure minimum. So for narrowband design, we maintain the things in such a way that at a desired frequency, over power match noise figure and noise match noise figure, they become almost equal and you get the minimum noise figure. For wideband design, we cannot do that. So this is a second big issue in the wideband design. So with this slide, we finish our quick review of the basics. Now I will talk about the type of LNA, and now we are 45 minutes, halfway into the seminar. So next 45 minutes I will be talking about the type of LNA, circuits of LNA, and the case studies of the LNA. So usually the target parameter for LNA is that S11 should be better than -15, noise figure should be less than 3 dB, linearity should be more than 0 dBm, gain should be flat over a desired band, and reverse isolation should be better than 50 dB, and this should cover entire band with the minimum power. What is the currency we have in our hand? There are two types of currencies for on-chip design. First currency is power, and second currency is the area of silicon. So we want the LNA to take small areas and also little power. Small areas becoming more important with the time because now we have a MIMO systems. So in massive MIMO system on the chip, we will be having say 64 antennas on a single chip. So imagine we have a 64 antenna and we have a 64 amplifiers. So if amplifiers are using the inductors, which is a classical way to design the amplifier, then the chip will be as big as a PCB. So we want the inductor-less designs so that the LNA size is smaller because we have put a lot of LNA on the same chip. So now in this case, our currency, which is the power, and second the silicon area, both are becoming very, very important. Let's look at, we will discuss the three types of LNA: narrowband LNAs, multiband LNAs, and wideband LNAs. So something like 8-9 years back, we have published a paper which is about the different type of LNAs, and this is a tutorial and survey paper. So if you want to see the more deeper detail into these LNAs, then you can refer to my paper, which is the state-of-art LNAs, and it's published almost 10 years ago. So narrowband LNA, if you look at this LNA, for time being, just assume this inductor is not there, this inductor is not there, this transistor is not there, and this L and C is not there. So what is it? It's basically a common source LNA. So why we put this inductor here and here? Because in case of common source LNA, the input is very high. It's a capacitance basically. But here we need a 50 ohm matching so that our S11 is better than -10 or -15 dBm. So we are using these two inductors here to compensate this capacitance so that this input become the 50 ohm. So there is no, these two inductors are having no role other than matching. So now here on the top we have one resistor here. So we are putting a filtering network. This is a narrowband LNA. So we are putting a LC tank here, which is a filtering network. So we want to optimize the gain at a desired frequency. And we do not want to use the resistor because resistor contributes to the noise. And secondly, if all current passes through the resistor drop will be higher, and in 1.1 volt, the voltage headroom problem will be there. Now the DC current is coming through the inductor and resistor is not contributing much into the current. So that's why the drop against the resistor will be smaller, and then we will be having the higher gain, and that gain will be actually the reactance of this multiplied by the GM. And then we are putting this cascode transistor just to improve the isolation, nothing else. So this is basically a common source circuit. The input inductors are put to put the matching. The cascode is to improve the isolation, and the L and C on the load side are there to reduce the voltage headroom and higher resistance for higher gain because the gain is GM multiplied by the load reactance. Yes, please.
Which part of the circuit is considered the load for matching?
The L, C, and R is considered as a load for matching. The first, this top element are the load for the matching. So let's look at the input matching. So if you look at here, L and C, so just write the equation V in here, and then this is the common source LNA, and this is the CGS at the gate, and I am just making the equivalent circuit of this one. So my V in is equal to I in S plus LG plus SS over 1 over SG and GMRC. So this is the Z input at this point. So the moment we cancel this SLS plus LG with 1 plus SG, what is left is the GMIG over CGS. So what we have left here is now at the resonance, when the both this L and S become equal to the CGS, we are left with the real part of input resistance, which is GM/LS over CGS. So here we have done the matching, and this factor gives us a 50 ohm match at the input. Similarly, from this design, we can calculate the gain and we can calculate the noise figure. I will not go into detail of this expression derivation. You can find it in the reference paper. So now this is a load network, and the load network, when we do the matching, this response will be a narrowband response, and if the load network has a Q, which is the 1 over WCR, then we have a response on the top, which is not a flat anymore, but it will give us a resonance response. So what is the advantage of narrowband LNA? The advantage of narrowband LNA is that this type of LNA gives the most optimal noise figure. We don't have any kind of LNA which has as good noise figure as this one, because we have a two filtering network, one at input and one at the load, and over all out of band noise is rejected, and we can have a noise figure as good as 1.2 dB, which is excellent noise figure from this kind of LNAs. The problem of this LNA is that these are narrow band. They work at a resonant frequency only, and then we cannot use it for wideband or multiband applications. The second type of LNAs are multiband. So instead of using the one resonance network, people propose that we use the multiple resonance network at input and multiple resonance network in the load. So we have a multiband response. And there is a concurrent LNA. This means that the multibands appear at the same time, and resonance in both the bands are taking place at the same time. And other is non-concurrent, means that this you are tuning the resonance network and you are taking at a one band and then you are moving to the another band. So let's see some example. Here you have a concurrent LNA. So you see on the here you have a one resonance network here, and second resonance network is this inductance with the CGS included. And similarly, you have a two resonance network here. One is a series resonance, other is a parallel resonance. So now you will have a one band and second band, and LNA will be amplifying at both the bands. So if you want, there is a references in the bottom. So I will share the slides and you can see these references and go in the details. So this is a non-concurrent LNA that now you are putting the tuning in here. You have put in the switch here and variable capacitor. So you variable capacitor here. So you can use the switch, or you can use the variable capacitor, which is basically a transistor connected in a diode fashion, or you can use both of them. So this design is called non-concurrent, that at one time the LNA will be amplifying only one band. So pseudo concurrent LNA is that you have a control of the matching here and control of the matching here. So this is the LNA's type of category, which is between the concurrent and non-concurrent. So now our last category is wideband LNA, and our case studies also deal with the wideband LNA. So wideband LNA are coming in a lot of different categories. We are talking about the need of 50 ohm matching at the input. So for the common source amplifier, 50 ohm matching is attained using the LC resonance network at the input. But if we want to avoid this inductance at the input, the very natural thing available to us is a common gate LNA. So because if you look at the gate of common gate LNA, the impedance is 1 over GM. And then you can size the transistor in such a way that this 1 over GM is a 50 ohm. So then you can naturally get the 50 ohm at the input without using the inductance. So this is the first we will talk about the common source amplifier, and then we will talk about the common gate amplifier, and then there are different techniques which are used in wideband LNAs. So first thing in wideband LNA is that we will avoid using the inductors, because when we have inductor and capacitor, there will be a resonance and response will be narrowband. And if we want to go to the wideband stuff, then we have to remove the inductors and reduce the capacitance as much as possible that our response is a flat response. So CS with a feedback network. So this is a LNA where you can put a 50 ohm to do the matching. What's the disadvantage of this type of network? You are doing the 50 ohm matching and you have just placed the 50 ohm resistor at the input. Noise figure will increase, power consumption will increase. Noise figure is the biggest disadvantage. We cannot do that. So what are the possible way is the feedback in these three different topologies. You can see here we have a resistor feedback, here we have a effective coupled feedback, here we have a parallel network feedback, and here with the feedback is here, we have one. This is a feedback network. How? Because VGS is actually V in here and minus V out here. So this actually a feedback inductor, and this has a coupled with this inductor. So these are all four feedback mechanism for wideband LNA: resistor feedback, RC feedback, parallel RC feedback, and transformer feedback. So we can get the 50 ohm input impedance using the feedback. Then common gate LNA, as I mentioned, that in this case the gate is common, and we are looking from the gate source terminal, and we see a 1 over GM, and that's how we get a Z in is equal to 1 over GM plus 1 over GMP. So if this expression is equal to 50 ohm, we will get a matching. Filter based LNA, that instead of putting the matching from the common gate, we put the different kind of filters, and then we can get a wideband response from the filters, and that filter are designed in such a way that they have a wideband. Then the very popular thing, and this distributed LNAs are coming back for the millimeter wave application. That is a distributed LNAs where you have a multiple transistors, small transistor. They are connected in a parallel fashion, and they make a kind of LNAs which are called the distributed LNAs. There's a two journal papers are given in the reference for this design. So let's go back and see the detailed look at the wideband LNAs. So there are these two types of LNAs. The moment you make the band wider, so the noise in the band is actually integration of the noise over a whole bandwidth. The total noise is total RMS noise is integration of the noise from the lower bandwidth to the higher bandwidth. So if you make the LNA which is wideband, noise figure will be very, very high. So first thing which was an issue using the wideband LNA was the large RMS are the large accumulated noise in a band at the output. So there's a group in the University of Twente in Netherlands, and this is a group of Professor Bram Nauta. They proposed first time the technique called the active noise cancellation at LNAs. So from their group, this technique was introduced to solve this problem, that now from the narrowband we are moving to the connectivity of wideband. So how to solve this problem? So they proposed that the noise can be actively cancelled inside the LNA. So this was this is a diagram from their paper, and this is how they explain it. That you have a noise at an input, and then this LNA is giving the noise, and you pick the noise from the node X, and then you add the noise in here in a reverse polarity. So the output, this output submission is in such a way that your signal adds up, but your noise gets cancelled. Remember, this noise cancellation has an underlying very strong assumption that this noise has to be correlated. We cannot cancel the noise of two uncorrelated resources. They always sum up. So this means the noise of the main transistor in LNA, which is amplifying transistor, when you transfer that noise to the output through the amplification path, this has certain polarity. And then you provide the second path either from the feed forward network or feedback network, and then you add at the output node in such a way that that noise polarity has reversed. And because this noise sources are correlated to each other, the cancellation will take place. If the noise are not correlated, the cancellation will not take place. So this is the main transistor. So here is a noise. So this noise is going through this feedback on this node, and this current noise is multiplying by the load and becoming on this node. So at the node Y, when you sum up the noise, it's cancelled. And when you sum up the signal, it's added. So this is a more detailed depiction of the same concept. That here you have a noise here. Now you have another feed forward path or feedback path. This is a feedback path and this is a feed forward path. This noise is coming here. This noise is coming from this path, and this is coming from this path. And you see this noise polarity is opposite of this noise polarity. So when you add up, this noise is cancelled, and this signal has same polarity, the signal is added. So this is the basic architecture of noise cancelling LNA, and this is the backbone of the wideband LNAs. You cannot make the wideband LNAs just without noise cancelling, because in that case the noise from whole the band will be integrated and noise figure will be very, very high. So this is the linearization and optimization technique. We will skip this one. The second important technique is the current reuse. I will just show in the case study this current reuse technique. So let's go to the case study directly, and we will go slow by slow. This is my own design, and this design was published in solid state circuit conference in 2007. So this is our measurement results. This is a wideband LNA from 1 to 7 gigahertz, and we have a nice figure of 2.4 at 3 gigahertz. And I will show very slowly, step by step, that how this LNA was designed. So you see here, this is your common source amplifier. Now in this amplifier, what is its gain? GM1 into RD, because M4 is nothing, it's just a cascade transistor. Now I need your attention. So I will go step by step at how. So what is input impedance here? It's a high. So first thing I need to make is that I need to bring this back to the 50 ohm. So for 50 ohm, what we did is we used a feedback network here. And if you carefully see here, what type of transistor is this one? What is this configuration of this one is common source. This is cascade. What is the configuration of M2? Anyone? Common gate. This is common gate. And when you look from this side, from R1 side, what will be the impedance here? 1 over GM plus R1. So we have selected R1 and 1 over GM of this M2 in such a way that we get here a 50 ohm. And what is this M3 doing? Just a biasing. This M3 is biasing this M2 in common gate configuration. And this is feedback, this is getting the signal from feedback from CCC to, so what we got here is Zin is equal to 1 plus GM R1 plus GM2 1 plus AB. So this is our input impedance here, and then we tuned it to the 50 ohm. So our first problem is solved. True? Now we are in 65 nanometer technology or 90 nanometer technology or 28. The voltage headroom is very, very small. Fine. So if the main transistor here for the gain is M1. So if we pass more current into it, let me go back one step. What I can do here, to increase the gain, I can either make the M1 bigger or pass more current through M1. So there's only two ways to increase the gain. Use the large W by L or put more power into the transistor. So if I put more power into the transistor, my gain is GM 1RD. So what will happen? My DC is coming here. So DC will pass through the resistance, and my ID RD drop will be higher, so that my M1 will go out of saturation. So I cannot pull more DC because my VDD is very small. So what I need to do, I need to provide, and I cannot make the M1 more bigger, because if I make the M1 more bigger, the parasitic will grow and my bandwidth will reduce. So these are two trade-offs. So what we did here is, I put it on other PMOS here, which is supplying the current to M1 bypassing the RD. So this is the additional current supplied to M1 so that M1 can have a higher gain, but that current should not pass through the RD so that it will not consume the voltage headroom. Got the idea? So now if this M5 is burning the power, so where this power is being used? This is burning the power, but this is DC, but this is not amplifying any signal. So why not to use this M5 as an amplifier as well? So this current is, you see here the current is coming from here. So the current passing through this one is sum of these three currents. So what I have done here is, I have taken the signal from the input and fed back to the gate of PMOS transistor, so that now it's giving additional current to the M1, so that M1 gain goes higher, but it was not amplifying itself. Now it has got an input signal from here to the M5, so M5 is also amplifying. So now I have the amplification, which is the gain of GM of M1 and also the GM of M5. So this means the current passing through M5 is used twice. First, it's giving its own gain, and secondly, same current is going to M1, and then it's giving the gain again. So from the current which is passing through M5, I am getting the gain 2 times. So that's called the current reuse. Where you see the input signal is here, and this is the my gain impression, where I have a GM1 and GM5 both amplifying the signal. So this is a half left side of the LNA. So the total, usually in the high frequencies, we make a differential signal for 2 reasons. The major reason is that we want to reduce the third order non-linearity, so we make the differential design. So now we switch to the differential design. So this is the differential. Now in this case, we have a left leg and right leg, which is amplifying V plus and V minus signal. but the bandwidth is reduced because of the additional capacitance and large transistor. So to improve the bandwidth, there is a technique called cross coupling. That if you have in differential signal, you have a one node going up and second node going down. So if you tie those nodes with the opposite capacitors, that's called the bandwidth extension technique. So here we have applied a CW capacitor, which is a opposite node, and this is called the bandwidth extension capacitor. So if we apply this bandwidth extension capacitor, then we will have a bandwidth extension. So now we have used the feedback techniques, 1 over GM, current is used, input to the signal, and bandwidth extension capacitor to do all extension of the parameters we have. Now what about the noise? So that is embedded inside it. So now look at the simplified circuit. So this is our simplified circuit. So this is the noise of the main transistor because this is the main amplifier. So this noise is now going back at this stage to this one. So what I have here is, this is my beta network, which is feedback, and this is my amplifier with a negative gain. So this is my load. So this noise, when it comes at output, V and square, this is multiplied by RD. So what I get at the output is the IN square bar multiplied by RD square. So this is my output noise at this node. So this is modeled in here. Got it? So this noise now, when this and the same noise goes back to this transistor, comes in here back, and then at the input this noise is there. So if I refer this noise to input here and this noise goes back to here, this both noise has opposite polarity and their net effect is reduced. So you can see here that this net effect is reduced and my total noise is 4 KT over GM, and this is divided by the gain of the amplifier. So this is the indirect noise cancellation which we are maintaining through the feedback network. So that's why the noise figure has come down. So now what about the linearity? So we have to have a better linearity. So for that linearity, so this is about the noise contribution of different. So total noise factor will be equal to noise contribution of this one, this one, this one, and this one. So noise of this M1 is cancelled to the large extent, and the other noises are adding up. But those noise contribution are very, very small. So overall noise figure is small for this LNA. Now, the last thing which we will discuss here is the biasing. So our linearity depends upon where we are biasing the transistor. You see here, this is G1, this is GM, and this increases with the VGS. And if I take the derivative, it's a G2. And if I take the derivative again, it's a G3. So the third order non-linearity is coming from the G3. So I have to bias the amplifier on the biasing point, DC biasing point, where my G3 is crossing the zero line. So at this point, if I DC bias my main amplifier, which was this amplifier, if I bias it at a 360 millivolt, my third order non-linearity will be very, very small, because when I selected the size of this transistor in such a way that my third order derivative is close to zero at my desired bias point. So you have to do a lot of iteration to match all these things close to your optimal. So now this design was actually manufactured. So now this design applies 6 different techniques for the biasing, ternary use, gain boosting, linearity optimization, and noise cancellation in a one circuit. So, and they are optimized close to the some global optimal. We don't know it's an optimal design, because even with this 10 transistor, you cannot explore all the permutation. So After the number of simulation and optimizing all these things, we manufactured this one, and these are the measurement results which are listed here. The voltage gain was 17 dB. The technology is 130 micrometer CMOS. The frequency range is 1 to 7. Noise figure is 2.4 at this gigahertz, and the power consumption is just 25 milliwatt. The active area is very, very small because this amplifier is using is not using any inductors. So this is our comparative results. And when it was published in 2007, this was the smallest reported LNA in the world, which was having the reasonable noise figure, power amplification, and the gain. After that, the much better LNAs are published after this design, which also refer this work. So this was a first case study, and second case study is I will pass through quickly because we are closing to the last 10 minutes of the seminar. So this is a LNA and Mixer Mixed. So we have a LNA and mixer in a merged form. So you see here, this is the same stage like earlier you have seen. This is the stage you discussed. And now with this stage, we have put a switching mixer here. This is a switching mixer. And we are driving with LO signals, which are LO plus and LO minus. And now it's amplifying and down converting in a one go. And then we have applied the same techniques. This is a linearity, the same techniques, cancellation GM3 linearity cancellation technique is applied here. So this is a second order for the N mass, and this is for P mass. And where it's passing close to the zero, this is a GM3, third derivative of the GM. So where they are going close to the zero line, that's the point where we bias them. So these are the measurement results of this one. So this is the input response. This is the gain curves. This is the noise figure, and the different combination when you have a different LOs and different frequency bands. So this is the comparison of the result with the state of art. You can see this paper, all the design published in this reference paper. So this, we get to the end of our presentation. So in this presentation, we defined about what is SDR, what is the challenging in SDR, what is a cognitive radio. We talked about the narrowband LNAs, we talked about the multiband LNAs, and then we talked about the wideband LNAs, and then we talked about in the detail the case study of a wideband LNA. So thank you very much. If you have any question, please let me know. So if you have any questions, please let me know. So
online audience can simply turn on your mic.
Any one of you in the lecture hall have any questions? You are more than welcome, please.